Many of you are familiar with the Pythagorean theorem, which says that in a right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. Today, I will go over this theorem, including how to prove it, inequalities that come with it, and some sets of integers that satisfy it. First, let's go over how to prove the Pythagorean theorem. Let's start with this figure. This figure is a square with side lengths a plus b, and a square inside it with side length c. The smaller square is bordered by four right triangles with legs a and b and hypotenuse c. We can write this larger square's area as a plus b whole squared. Expanding this, we get a squared plus 2ab plus b squared. We also know that the four right triangles each have an area of 1/2 AB. Combining four of these, we have an area of 2AB. This leaves the square with side length c, which has an area of c squared. This figure shows us the second way of writing the area. We can now equate these area formulas, giving us that a squared plus 2ab plus b squared equals c squared plus 2ab. We can subtract 2ab from both sides to get the Pythagorean theorem, a squared plus b squared equals c squared. Now, let's talk about the inequalities that come with the Pythagorean theorem. In a right triangle, a squared plus b squared is equal to c squared, but in other types of triangles this is different. In an acute triangle, for example, we know that a squared plus b squared is greater than c squared, where c is the longest side. And in an obtuse triangle, a squared plus b squared is less than c squared, where c is the longest side. These inequalities allow you to classify a triangle as acute, right, or obtuse based on its side lengths. Next, let's talk about sets of integers that satisfy the Pythagorean theorem. These sets of integers are called Pythagorean triples or triplets, and they are sets of three integers listed in ascending orders, where the square of the first two adds up to the square of the third. The most famous triple is 3, 4, 5. 3 squared plus 4 squared, which is 9 plus 16, is equal to 25, which is 5 squared. Any multiple of a Pythagorean triple by a scale factor also forms a Pythagorean triple, so we can form more triples from this one, such as 6, 8, 10, 9, 12, 15, 12, 16, 20, or 15, 20, 25. The next most common triple is 5, 12, 13, where 25 plus 144 equals 169. After this comes some less common triples, such as 7, 24, 25, 8, 15, 17, 9, 40, 41, 11, 60, 61, and so on. Pythagorean triples that are not multiples of other triples are called primitive Pythagorean triples, and there are an infinite number of these. Lastly, let's talk about how to generate Pythagorean triples. This formula will only generate primitive ones, but you can multiply any of these by any scale factor to get non-primitive triples. The formula requires two distinct integers, m and n, that differ by 1. In this formula, a is equal to m squared minus n squared, b is equal to 2mn, and c is equal to m squared plus n squared. If n is greater than m, then you should make a equal to n squared minus m squared instead. Using m equal to 1 and n equal to 2 in this formula gives us 3, 4, 5. Using m equals 2 and n equals 3 gives you 5, 12, 13. Try this formula out for yourself by putting in two numbers that differ by 1. I hope you enjoyed this video about Pythagorean triples, and I'll see you next week for another one.